White dwarfs represent one of the final stages in the life cycle of a star. These fascinating remnants of stellar evolution are both a testament to the forces governing the universe and a window into the processes that dictate the life and death of stars. This article delves into the formation of white dwarfs, exploring the physical mechanisms, the evolutionary pathways, and their significance in the broader context of astrophysics. To understand the formation of white dwarfs, it is necessary to first examine the life cycle of stars. Stars form from vast clouds of gas and dust, known as nebulae, through the process of gravitational collapse. As the material collapses under gravity, it heats up and forms a protostar. When the core temperature reaches approximately 10 million Kelvin, nuclear fusion ignites, converting hydrogen into helium and releasing immense amounts of energy. This marks the birth of a main sequence star. Main sequence stars, which constitute the majority of stars in the universe, sustain themselves through the fusion of hydrogen in their cores. The balance between gravitational contraction and outward thermal pressure from fusion defines the stability of the star during this phase. The amount of mass a star possesses plays a critical role in determining its evolutionary pathway and ultimate fate. The formation of a white dwarf is the endpoint for stars with initial masses between approximately 0.5 and 8 solar masses. These stars are not massive enough to end their lives as neutron stars or black holes, but are too massive to simply fade into obscurity as brown dwarfs. Their evolutionary path involves several distinct phases. As a main sequence star exhausts its core hydrogen fuel, nuclear fusion ceases in the core. Without the outward pressure generated by fusion, the core contracts under gravity and the surrounding layers of hydrogen begin to fuse in a shell around the core. This process causes the outer layers of the star to expand and cool, transforming the star into a red giant. For a star like the Sun, this phase is expected to last several 100 million years. During the red giant phase, the core continues to contract and heat up. For stars with masses below about 8 solar masses, the core temperature does not reach the threshold required to fuse carbon and oxygen. Instead, helium fusion occurs in the core, producing carbon and oxygen as end products. After the red giant phase, the outer layers of the star are ejected into space, forming a planetary nebula. This ejection occurs as a result of pulsations and strong stellar winds driven by the radiation pressure from the hot core. The planetary nebula phase is short-lived, typically lasting tens of thousands of years, and represents the final stage of mass loss for the star. What remains after the planetary nebula dissipates is the hot, dense core of the star, a white dwarf. White dwarfs are composed primarily of carbon and oxygen, with trace amounts of heavier elements if the progenitor star underwent advanced fusion processes. The absence of further nuclear fusion means that the white dwarf is supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle. White dwarfs are extraordinary objects governed by unique physical principles. Their properties offer insights into the interplay of quantum mechanics and gravity. The key to a white dwarf's stability is electron degeneracy pressure. In a white dwarf, the density is so high that electrons are forced into close proximity, creating a state where no two electrons can occupy the same quantum state. This degeneracy pressure provides a counterforce to gravitational collapse, allowing the white dwarf to maintain a stable configuration despite its lack of energy generation. The Chandrasekhar limit, approximately 1.4 solar masses, represents the maximum mass a white dwarf can have while remaining stable. Above this limit, electron degeneracy pressure is insufficient to counteract gravity, leading to the collapse of the white dwarf into a neutron star or a black hole. This limit plays a crucial role in the evolution of binary systems and the occurrence of type Ia supernovae. White dwarfs are incredibly dense, with masses comparable to the Sun compressed into volumes similar to that of Earth. Their composition depends on the mass and fusion history of the progenitor star. The most common white dwarfs are carbon-oxygen white dwarfs, but helium white dwarfs and oxygen-neon white dwarfs can also form under specific circumstances. Astronomical observations provide a wealth of information about white dwarfs and their properties. These remnants are typically studied through their luminosity, temperature, and spectra. White dwarfs do not produce energy through fusion. Instead, they radiate their residual thermal energy into space. Over billions of years, they gradually cool and fade, transitioning from a bright, hot state to a dim, cold one. The cooling rate of white dwarfs depends on their mass, composition, and the presence of crystallization processes in their cores. Many white dwarfs exhibit strong magnetic fields, which can reach strengths of millions of Gauss. These fields are thought to arise from the conservation of magnetic flux during the contraction of the progenitor star. Additionally, white dwarfs have relatively rapid rotation rates, although they spin more slowly than their progenitor stars due to angular momentum loss during the mass ejection phases. White dwarfs are classified based on their spectra, which reveal their surface composition and temperature. Common spectral types include DA, which have hydrogen-dominated atmospheres, and Db, which have helium-dominated atmospheres. The spectral features provide clues about the processes that shape the white dwarf and its cooling history. White dwarfs in binary systems can undergo unique interactions with their companions, leading to phenomena such as nova outbursts and type Ia supernovae. A nova occurs when a white dwarf accretes material from a companion star, typically a red giant or main sequence star. As the material accumulates on the white dwarf's surface, it undergoes thermonuclear ignition, producing a sudden and dramatic increase in brightness. Novae are recurring events, as the white dwarf can continue to accrete material after each outburst. If a white dwarf in a binary system accretes enough material to exceed the Chandrasekhar limit, it undergoes a catastrophic collapse and thermonuclear explosion, resulting in a type Ia supernova. These events are vital tools in cosmology, serving as standard candles for measuring cosmic distances and the expansion rate of the universe. White dwarfs play a significant role in the chemical and dynamical evolution of galaxies. Their mass loss during the planetary nebula phase enriches the interstellar medium with elements like carbon, nitrogen, and oxygen, which are essential for the formation of new stars and planets. Additionally, the cooling of white dwarfs provides a long-term record of star formation history in galaxies. The formation of white dwarfs is a natural consequence of stellar evolution for a significant fraction of stars in the universe. These dense, compact remnants embody the intricate interplay of nuclear fusion, gravitational dynamics, and quantum mechanics. By studying white dwarfs, astronomers gain valuable insights into the life cycle of stars, the chemical enrichment of galaxies, and the fundamental physics governing the universe. As observational techniques and theoretical models continue to improve, our understanding of white dwarfs and their role in the cosmos will undoubtedly deepen, shedding light on the enduring mysteries of the stellar life cycle.